The first thing we want to discuss is the limitation of the support confidence framework. As we know, pattern mining may generate a large number of rules, but not all of the patterns and rules generated are interesting. In general, we can classify the interesting measures into two classes, objective versus subjective. For objective measure, like support, confidence, correlation, are defined by mathematical formulas, not change from person to person. But the subjective measure may change from person to person because one man's trash could be another man's treasure. So the first thing is we may want a user to say, what do you like to see? So it's query-based. Another thing is we may, based on users' knowledge base, try to mine something unexpected, fresh, or recent. Or we can map patterns and rules into two-dimensional space, let user to interactively pick some interesting things. So we know we have support and confidence as two interestingness measures in association rules. So we may be careful about this because not all the strong support and confidence rules are interesting. For example, take the following table as two-way contingency table to look at this to see how to interpret things we found. For example, in this table, 400 out of 1,000 students playing basketball and eating cereal. But 200 students, they play basketball, but they may not eat cereal. Okay. In this one, you may derive an association rule like this. Playing basketball implies eating cereal. You probably will get 40% support because it's 400 over 1,000. You will get 2/3 of the confidence because you get 400 over 600. So this is pretty high support and confidence. Is this rule interesting? We may try another rule we generated. Actually, you will see if we say not playing basketball, eating cereal, you will see not playing basketball is 35%, but the confidence even higher because they have 350 eating cereal out of 400 people. So this one is even higher. So if you recommend these two rules to the cereal company, okay, they will get confused. They say, oh, the first rule said I better give them free basketball because if they play basketball, eating cereal. The second rule say I better take their basketball away because if they do not play basketball, they actually eat cereal even more. Which one is right? Let's examine it. We have learned support and confidence, these two measures, are not sufficient to describe association rule. So the problem becomes, what are additional interesting measures good enough to describe their relationships? So that's the reason we want to examine a little more, like a lift and a chi-square, whether they are good enough to describe as additional interesting measures. So lift has been popularly used in statistics as well. We look at the same table. Okay? The same table, we can think B means playing basketball, C means eating cereal. So we have the exact same distribution. Then for this contingency table, we can use lift to compute it. The lift is defined as this. B and C are two item sets. For rule B implies C, that confidence, if it's divided by C support, we get lift. Or we can say if BC, this rule's support divided by B's support times C's support. Okay. So for this lift, the general rule is if the lift is 1, then these two items are independent. If it's greater than 1, they are positively correlated. If it is less than 1, they are negatively correlated. For our example data set, we will calculate the lift of B and C, and B and not C. We derive 0.89 and 1.33. Okay. Then from this data sets and the rules, we can see B and C should be negatively correlated because the lift is less than 1. B and not C are positively correlated because the lift is greater than 1. This actually fixes our problem because we know B and C should be negatively correlated. B and not C should be positively correlated. So this looks very nice. Let's look at another measure popularly used in statistics as well, called chi-square. In chi-square, the definition, we need to calculate the expected value. Okay, how to calculate expected value? You probably can see this 400 is a real value, it's observed value. But expected value is just based on the distribution. For example, C and not C, the distribution is 700 over 250. This is 3 to 1. Among 600 students, the 3 to 1, you will get 450 versus 150. In that case, we probably can see we still can use the rules, like if chi-square is 0, they are independent. It's greater than 0, they are correlated either positively or negatively. So we need additional tests to see whether they are positively or negatively correlated. Now for our example, we can easily calculate chi-square should be almost 76. So B and C should be correlated. Further, we can say they are negatively correlated because the expected value is 450, the observed value is only 400, it's less. So these themes can solve the problem as well. But the problem becomes whether lift and chi-square are good in all the cases. Let's examine some interesting case. In this case, you probably can see this not B, not C actually is quite big. There are 100,000. Okay, these actually call null transactions because the transaction contain neither B nor C. And if we just look at B and C relationship, we probably see B and C should be negatively correlated because it's not easy to get B and C together. B and not C is far bigger. C and not B is also far bigger. But if we use the lift, we compute the lift B and C, we'll get this 8.44, which is far bigger than 1. That shows B and C should be strongly positively correlated. This seems not right. Even we try to use this same contingency table, we add the expected value, we do the computation, we will find chi-square is bigger than 0. In the meantime, the observed value is far bigger than expected value. So we also should say B and C are strongly positively correlated. This seems to be wrong. What's the problem? Actually, there are too many null transactions that may make things distorted. We need to fix it. We already seen lift and chi-square may not be very good measures examining the transaction data that contain lots of null transactions. So what we may like to see is what are good measures. They do not influence much by number of null transactions. Let's look at those different measures. Some measure, they have the property called null-invariance. That means their values may not change with the number of null transactions. Okay. Let's see what measures are null-invariant, what measures are not null-invariant. We already know chi-square and the lift, they are not null-invariant. Their value change with number of null transactions. But people have found that the following 5 measures, if you check their formula, their definition, they are actually null-invariant measures. So you probably know Jacquard coefficient and cosine measure quite well. These 2 measures are popularly used, they are null-invariant. But all confidence, which actually take the smaller value among A and B as the denominator, the numerator is just the transaction support, the support of the rule. So the max confidence is trying to find the maximum one of them. These 2 actually were proposed in the study of measuring association rules. Kruzinski measure was proposed around 2007 by our group. We originally called these as balanced measure, but later the reviewer actually pointed out that this measure was actually proposed by a Polish mathematician called Kruzinski in 1927. So we changed the name of this measure to Kruzinski measure. Let's first look at null-invariance, why they are very important. That means why in analysis massive transaction data, the null-invariance is so critical. Because in many transactions, the transactions that contain particular sets of items, the chance actually is very rare, like Walmart transactions. They may contain neither milk nor coffee. When you try to analyze milk and coffee using the following contingency table. So this MC means the number of transactions that contain both milk and coffee. This not M not C means the number of transactions that contain neither milk nor coffee. So this not M not C is the number of null transactions. Then we see lift and chi-square, they are not null-invariant, so they are not good at evaluating data that contain too many or too few null transactions. For example, we just look at this, okay? For this data set D1, MC means number of transactions that contain both milk and coffee. Not MC means the number of transactions contain no milk but coffee. M not C means the number of transactions that contains milk but not coffee. Not M not C means the number of null transactions that contain neither milk nor coffee. Okay, so you probably go to like a Walmart, this kind of shopping market. You probably will see there could be the cases you get 10,000 transactions that contain milk and coffee, but 1,000 contain not milk but coffee, 1,000 contain milk but not coffee. In that case, you probably say, actually, likely if people buy milk, they would buy coffee as well because there are 10,000 such cases. By only one of them, it's only 1,000. But if you have a lot of null transactions, this value could be quite positive. If you have very few null transactions, it turns out they are independent. You probably look at the value, they are not independent. On the other hand, if you see there's only 100 cases you got milk and coffee together, there are many more cases they buy it alone. But once you have many null transactions, it turns out to be very positive. The number is quite big. So no matter you get very many null transactions or very few null transactions, something may go wrong. Okay. So we do need to analyze such data using some null-invariant measures. Okay, we'll examine this in more detail. Now we come down to compare those null-invariance measures. So which one is better? We know we probably can sense not all those null-invariant measures are created equal. So we want to see which one is better in all the cases. Let's examine the two-variable contingency table on the transactions containing milk and coffee. Let's look at the case in this data set. So the first, you look at D1 and D2. D1 and D2, you probably can see the differences are only on the number of null transactions. But you also can see very likely milk and coffee should get together. They should be positive. In that sense, you probably see all those 5 null-invariant measures, they give equal value in the sense no matter how many transactions on the null part, okay, they do not change their value. And also they are very close to 1 in the sense these are possibly getting together. Then you look at D3. D3 means MC getting together is quite rare because they get alone actually is more frequent. In that sense, all their values are very close to 0. Then you look at D4. D4 says MC getting together or MC alone, they are all like 1,000, 1,000, and 1,000 cases. No matter how many null transactions, they actually got things right in the middle. This 0.5, 0.5, only Jacquard 0.33. Actually, this in Jacquard, this one means it's balanced. It's right in the middle. Then we look at trickier cases. It could be D5 and D6. D5, if you see this is 1,000, 100, and 10,000 cases. So what you probably can see is from coffee point of view, like a coffee guy may say, oh, MC are likely getting together because they get along is 100 cases buying coffee, but not milk. 1,000 cases, they buying both coffee and milk. But from milk guy, they probably say, oh, they are very unlikely getting together because I got 10,000 cases buying milk, but not coffee, but only 1,000 cases buying milk and coffee. So in that case, you look at different measures. It's interesting. You see all confidence and Jacquard, they also say it's closer to 0. They are unlikely getting together. But max confidence says it's close to 1. They are very likely getting together. Then we look at Kruzinski said, I'm right in the middle because the tug of the war, each side is 10 to 1. Then cosine said, I'm a little prone to unlikely getting together. Now we change this one even more. This is 1,000 to 10 or 1,000 to 100,000. The coffee guy said they are very, very likely getting together, but milk guy said they are very unlikely getting together. Now in this case, you can see all confidence and Jacquard drop down to 0.01, and even cosine drop down to 0.1. But the max confidence says, I'm very confident they are very close to 1 because they're very likely getting together. But Kruzinski said, I'm still in the neutral because this is 100 to 1, the other is 1 to 100. They have the equal ratio. So which one do you like? So probably we can see D4 to D6 are the real cases that differentiate the 5 null-invariant measures. But we probably can see Kruzinski measure holds firm when in this very imbalanced cases, but the ratio is balanced on both sides, and it holds firm at 0.5. That looks interesting. But on the other hand, we also know those cases, some are very imbalanced. We may want to introduce another measure called imbalance ratio. The imbalance ratio is introduced in the sense the support of item set A and support of item set B, their differences play an important role in this imbalance ratio computation. Then you perhaps see for the same cases, in the last 3, the Kruzinski measure holds firm at 0.5, but the imbalance ratio, okay, the D sub 4 cases is 0 because they are really balanced. And D sub 5 cases become 0.89. They are rather imbalanced. And D sub 6 cases, it is very imbalanced. So imbalance ratio really can show you, how balanced the two sides are. So we feel Kruzinski plus imbalance ratio, these two things getting together will present a clear picture for all the 3 data sets, D4 through D6. Because D4 is neutral and balanced, D5 is neutral but imbalanced, and D6 is neutral but very imbalanced. Okay. Finally, we are going to show you some real data sets, like DBRB data sets. We want to look at co-author relationships. So let's look at this table. This table we got around the year 2007. We study the recent database conferences. We look at those authors. They publish papers and they co-author papers in database conferences. But you probably can see the interesting thing is, for example, you look at Hans-Peter Krieger and Martin Pfeiffer. Martin Pfeiffer got 18 papers, but all of them are with Hans-Peter Krieger. But Hans-Peter Krieger got 146 papers, 18 was with Martin Pfeiffer. Well, you can see in that cases, Kruzinski shows pretty strong value. That simply says these two authors are closely tied together in some way, but they are imbalanced as well. You can see that based on imbalance ratio, you can easily calculate their imbalance ratio is reasonably high. So in that case, you probably can easily judge Hans-Peter Krieger likely to be the advisor of Martin Pfeiffer. So using Kruzinski and imbalance ratio, we can easily find advisor-advisee relationships and close collaborators. In one research paper on finding advisees, we are really using those measures to find them with reasonably high accuracy. So finally, we will show you a bunch of papers. These are the papers quite representative on how to judge the correlation relationship, the different measures, including the interesting measure on the null-invariant ones, and the measure we discussed on the Kruzinski. Thank you.